All right, so test 2 for statistics 2023. We got 20 questions to hit up. So let's get started. Covers chapter 4 through chapter 6. So our first question here, they give us a nice little graph, and it says to determine whether it shows an increasing trend, decreasing trend, a changing trend, or very little trend. So looking at this, here's our scatter plot. What do you think? Definitely increasing, because as the age of students goes from left to right and the value of the car moves from down to up, everybody's going in an increasing direction. So definitely increasing, which will be your bottom box. Perfect. Cool. So moving on, question 2. A lot of these first 4 to 5 questions are all about the trends and everything like that, as we saw in class. So here we got a scatter plot of shoe size and GPA for college students. So again, it's asking us, does it show an increasing trend, decreasing trend, no trend? Is there a strong relationship? So as we see shoe size and GPA, what do you notice? There is no trend whatsoever. These are just a bunch of dots going nowhere. So there is no trend. Okay? And then it says, so the graph shows no linear trend since the points show blank. Are they no, increasing, or decreasing pattern? Yeah, no, right? If you have no trend, then there should be no pattern. Okay? So there is no pattern by scanning the graph from left to right. The relationship is or is not strong then. So if there's no trend, what do we know about the relationship? Not strong. So is not strong. Definitely, because the points blank show or do not show consistent and small vertical spread. Do not show. That's right. I mean, the moment you start answering no, everything else along the lines pretty much becomes no. Okay, so no trend means that there's no pattern. Not a strong relationship means that there is no consistency and no vertical spread. Or no small vertical spread, I should say. Okay. Well, let me make sure there wasn't another question attached onto this one. I think that was it. Yeah. Question 3. So again, part A, it's asking us about the trend. And then part B, it'll want us to explain the trend. So we got a scatter plot of the number of hours worked per week and the number of hours slept per week for some college students. So, does the graph show increasing, decreasing, or no trend? No trend, or in this case, it would be what we call very little. Very little trend. Okay? And so down below, we need to explain that. So, A says students who work more hours tend to get fewer hours of sleep. Students who work more hours tend to get more hours of sleep. The number of hours of work is less than or equal to the number of hours of sleep for these students. The number of hours of work does not seem to be related to the number of hours of sleep. So we said there's very little trend. So which one of these represents that very little trend? That's right, they're not related. D. If there is no trend, then that means there does not seem to be a relationship between them. Perfect. Absolutely. Question 4. So the figure shows a scatter plot of birth rate and the age of mothers in the United States. Would it make sense to find the correlation for this data? Would it make sense to find that R? Explain, according to the graph, at what approximate age does the highest fertility rate occur? So, here's our graph. And would it make sense to find the correlation for this? So A says, no, it wouldn't make sense to find the correlation because there's not enough data points. Yes, it would make sense to find the correlation because there is a trend. No, it would not make sense to find the correlation between the trend because the trend is not linear. Yes, it would make sense to find the correlation because both variables are numerical. So there's our scatter plot. Is it wise to find our correlations? No. So it's either A or C then. Which one makes more sense? C. Yeah, because it's not linear. Remember, we harped on this in class that if you're going to find correlation, if you're going to do this, it has to be linear in nature. Super important for that. Cool beans. All right, number 5. Number 5. So here, this is where we're actually going to start getting into that correlation coefficient now, the R value. And so at number 5, they give us 3 scatter plots, and they have calculated the 3 R values for these, negative 0.94, 0.66, 0.03. And we want to determine which scatter plot goes with which one, which correlation coefficient. So we've got A, B, and C up here. So negative 0.94, 0.03, 0.66. Which one of those numbers represents the correlation coefficient for A? 0.03. You bet. Because remember, when we do our correlation coefficient, that R value, it is between -1 and a +1. And remember when we talked in class that the closer you are to 0, it shows no trend. Very, very weak relationship. The closer you are to a +1 shows you that positive linear relationship, that positive trend. The closer you are to the -1 shows you the negative linear relationship, the negative trend. All right, so B. Yeah, 0.666 because it's in the positive direction. It looks like it is going upward. And the only one that is positive down there that we can use is the 0.666, which makes sense also because the dots are a little bit more spread. The closer you are towards 1, the closer your dots will be. The closer you are towards -1, the closer your dots will be in your scatter plot. Very little vertical spread. So then obviously process of elimination, C has to be the negative 0.94, and that makes sense because that almost looks like a straight line. There's very little vertical spread there. Cool. All right, number 6. So it says below, the scatter plot shows the heights of mothers and daughters, complete parts A through E. So they give us the equation that's right here, so that's important to us. So they give us the equation right there. And then it says, as the data are graphed, which is the independent and which is the dependent? So up here, who is the independent variable, the mother or the daughter? That's right. Whoever's along this x-axis, that's your independent. So the mother's height is the independent. Then obviously that narrows it down for dependent. So dependent ends up being the daughter's height. And again, that makes sense because it's along the y-axis. All right, so now using the graph, from the graph, approximate the predicted height of the daughter of a mother who is 65 inches tall. So it says round to the nearest inch. So if we are 65, see if I can use a nice little kind of draw tool in here. Adjust that over. Wow, it doesn't really let me, there we go. Well, It was there. Doesn't really let me adjust over, so let's not do that then. Let's erase that guy. We'll try and draw it in as best as I can. Close enough. And then kind of drawing that over. So what do you think that height is rounded to the nearest inch? 66, probably maybe 67. So 66 or 67. I think probably around there because my lines weren't exactly straight. Okay. So from here it says, from the equation, determine the predicted height of the daughter of a mother who is 65 inches tall. This time it says round to 2 decimal places. So we're going to take the 65 and do what?
Multiply it, and I got 66.12.
66.12? Yeah. Take that 65 and we plug it right up in here into this equation that I had on the screen. So you're basically taking 23.87 and adding 0.650 times 65. And then you did your rounding and you said we got 66.12?
Oh, I didn't round it.
Oh.
That was just the natural answer.
Okay. So we plugged all that in, we multiplied, and it says round to 2 decimal places. So what did you say?
66.12.
66.12 is good. Which kind of goes back and verifies that, yeah, we were probably right with putting 66 up here. So you can use part C to help you verify your part B. And if you need to adjust, you know. So make sure that these 2 answers match each other relatively closely, according to rounding. Okay? So now it says, interpret the slope. So up here, who was our slope in that equation? Yes, the number next to mother.
Oh.
The number next to mother. So this is our end. That's our slope. And remember in class, what did I tell you is special about this slope? For each 1 unit of what? It's okay. So each 1 unit of the x, what does it tell us about the y?
That we're going to have 1 more of the y?
Well, maybe 1 more of the y, but it's our number, it's our slope, but it's the average of the y. Okay? So as we increase 1 unit of the x, we get this new average of the y. That's what the slope is all about. The average of the y value for every 1 unit of x. Okay? The average of that y value for every 1 unit of the x. So when we look at this, we need something that talks about the average of the y idea for every 1 unit of the x idea. So when we read the first guy, it says, for an additional inch of the mother's height. So the mother's height, is that our x value? Are you sure? Yes, it is. So this is so far so good because that's talking about 1 unit of x. The average daughter's height increases by 0.650 inch. So is 0.650 our slope? And is that talking about our y value? So that's our answer. Has to be A. Because this is talking about for every 1 unit of our x, we get the average y value. And if you look at the other ones, you can see that it doesn't make any sense. So like for part B, it says for each additional inch of the daughter's height. Well, that's adding 1 unit for the y value. You got to throw that out because it's 1 unit for the x value. C says the average daughter's height is about 0.650 times the height of the mother. This one, it's close to being right, but the problem is that it's actually talking about how you get the average value. And we want to know just about the slope. Okay? So while this uses the slope, it doesn't tell us about the slope. And then the last one says the height of the average mother, and that doesn't make any sense because we don't want to know about the average X. We want to know about the average Y. Okay, and then one more question. What other factors besides the mother's height might influence the daughter's height? Select all that apply. So remember, as we talked in class, when they put that select all that apply, you're looking at more than one answer. So the daughter's nutrition during formative years. Would daughter's nutrition affect your height? Absolutely. Because if we're not eating properly, we're not going to grow properly. Okay? And what about the father's height? Would that affect? Absolutely, because you get some of your mother's genes, you get some of your father's genes. That's going to affect your height. What about the heights of the daughter's siblings? No, we don't care about the daughter's brothers and sisters. Their heights do not affect her height. And then the number of children the mother has had in the past. No. Number of children the mother has had in the past doesn't affect it at all. So it's A and B. Nutrition and father's height. Okay. So question number 7. Question number 7, a lot of information in this one. So they want you to fill in the blanks with the equation. And they give us lots of information right above that. So you can see all the different pieces that they used in order to get to the equations. And we're going to talk about all these different technology uses and how you can identify the slope and identify the y-intercept. So with that being said, we're looking at the measurements that were made of a sample of adult men, assuming that the association between their hand length and foot length is linear. Output for predicting foot length from the hand length is provided from several different technologies, as I said. So the first thing says, report the equation for the predicted foot length and hand length. Use the variable names foot L and hand L in the equation rather than X and Y. So when you're looking at this information, right here is a key sentence for us. Output for predicting foot length from hand length. Who is the independent variable? Foot length or hand length? Hand length is your independent variable. So that means that foot length is our dependent variable, which makes sense because right here it says predicting foot length. When you are predicting something, that's your dependent guy. Okay? So when we're down here, who goes right here in the first blank? The predicted hand length or predicted foot length? The foot length. Because this is what we're trying to predict. Okay? So then over here in our next two blanks go a round to 3 decimals as needed. So we need to start looking at our numbers. So let's take this information that we have right here. So who goes in that first blank? Sorry, I should say the second blank. 14.57. And I agree. Because you can come up here and you can look right here. There's that first blank number. You could look right here. Well, I keep saying first blank, second blank number. There's our second blank number. Okay, not so much as visible in this guy, in the bottom guy right here, but those two right there tell you exactly who should be going in that first blank. So second blank. 14.57. Actually, it says round to 3 decimal places. So we should fix that. 14.572. There we go. So let's make sure that we watch that fine print so that way we don't get any errors, stuff incorrect because of simple rounding errors. So watch that fine print. And then who goes in the third blank? You got it. Good job, Rebecca. 0.654. Using this information that's right there. So we put 0.654. And then the fourth blank, again, it's another kind of multiple choice. Do we put hand length or foot length? Hand length, because we already used foot length. So there's our equation. Perfect. So again, we go back to that question on part B, how to find the slope and the intercept when provided different outputs, different technologies. So right here, we are provided this regression equation is such and such. So it says the slope is the constant and the intercept is the number being multiplied by hand length. The slope is the constant and the intercept is the number being multiplied by hand length divided by sample size. The slope is the number being multiplied by hand length and the intercept is the constant divided by sample size. The slope is the number multiplied by hand length and the intercept is the constant. Which one of these is it? A, B, C, or D? Based off of that output. Has to be D. You got it. When they say constant, that means the number that's by itself, no variable next to it. So when you're looking at these first two, these don't make any sense because we know that slope is never a constant. We know that it is always next to your variable, whatever you're looking for. So, and you already told me earlier that this guy, when we wrote our equation, was our slope. So we know that that's not the constant. And then the other thing that throws out C is nothing up here is divided by sample size. There's no division going on in that equation at all. So definitely D. Perfect. All right, so again, another one. Explain how to find slope and intercept for this displayed output. So our choices are the value of R is the intercept. Slope is the constant in the fourth line. In the fourth line, the slope is the constant and the intercept is multiplied by the hand. In the fourth line, the slope is multiplied by hand L and the intercept is the constant. And in D, the R value is the intercept and the slope is multiplied by the height in the fourth line. What do you think? Definitely C. Let's talk about what they mean by this fourth line thing. So when you're looking at this, each line, like this is line 1 right there. Simple linear regression results, that's line 1. Dependent variable foot L, that's line 2. Independent variable hand L, that's line 3, 4, 5. So each row of output is what they mean by the line. Okay? So when it says fourth line, you're looking at this equation part right here. And as we discussed in a lot of these other ones, you know, we throw out A because it's saying slope is a constant. But it also, right here, R value does not represent intercept. R value means that's our correlation coefficient. So, and then part B, again, it says slope is the constant. That doesn't make any sense. In part D, it says the R value is the intercept. Again, that doesn't make any sense because R value is your regression. So here we got another one. It says, explain how to find the slope and the intercept. So it says the slope is the intercept value divided by the x variable value, and the intercept is the intercept value. B, the slope is the x variable value, and the intercept is not given. C, the slope is not given, the intercept is the intercept value. Or D, the slope is the x variable, and the intercept is the intercept value. Say it again. Definitely D. Yeah. This x variable is kind of the word slope in disguise. Definitely. And the intercept has to be the intercept value. So that's why you can throw out a couple of the extra beginning ones. All right. And last but not least, explain how to find the slope and intercept for the displayed output. So this is what your calculator would show you. This guy right here is what your StatCrunch would show you. So right up in here it says the R value is the intercept, the B value is the slope, the R value is the intercept, the A value is the slope, the A value is the intercept, the B value is the slope, or the B value is the intercept and the A value is the slope. Which one is it? Definitely C. Yeah. Remember how we kind of talked about this in class? They like to write y equals mx plus b backwards. So they put the intercept first and then the slope value. So definitely is C. And you knew that from A and B we could throw those out because R values can't be intercepts. They're the correlation coefficient. Perfect. And I believe that should be, yep, it was the last question on that one. All right, so jumping into this bad boy. Number 8. Graph's a little gritty, but that's okay. So the equation for the linear regression line relating the salary and the first year employed is given by the figure. Okay. Report the slope and explain what it means. Either interpret the y-intercept of 4,255,424 or explain why it is not appropriate to interpret it. So here's our information. We can see our negative trend. We've got our equation right there for predicted salary based on your start year. So the first things first, we want to interpret the slope. So remember when we talk about the slope, what was the interpretation in general of slope? For 1 unit of x, we talk about the average of y. That's right. All right, so A says the salary of $2,099 would be the salary for a person who started in the year 2010. The average salary is $2,099 less for each year later that the person was hired, or an average of $2,099 more for each year earlier. A salary of $2,099 would be the salary for a person who started at the year 0. Or D, the average salary is $2,099 more each year later that the person was hired, or the average salary of $2,099 is less for each year earlier. Which one? Has to be B. Yeah. They actually, on B, they interpreted the slope both directions, but this is really what our slope is all about in our equation. That for every year later, you're losing $2,099 on average. You got it. Yeah. The less for each year, because exactly as you said, we have that subtraction that's going on. So that means we have to have some sort of relationship when we talk about the slope that is decreasing. If it was a plus, then we talk about it increasing. All right, perfect. So then now we talk about that intercept. So we've got A, the y-intercept of 4,255,424 would be the salary for a person starting after 2000. The y-intercept of roughly $4 million would be the salary for a person started prior to 1985. Or C, the y-intercept 4 million would be a salary for a person starting in year 0, which is not appropriate to interpret. Yeah, definitely C. Because at year 0, not working at all, my salary is $4,255,424. I wish. But yeah, that doesn't make any sense. Just don't make no sense. All right. Number 9. So data was collected to include information on the weight of trash in pounds on the street one week and the number of people who lived in the house. So we have our scatter plot. We're going to answer some questions about it. So they give us our equation right here. They give us the R squared value, all those things to keep track of. So first things first, is the trend positive or negative? And what does that mean? So that's right. It is positive because the number of people per household increases, so the weight of trash tends to increase, like what you said. Everybody's got to increase. Okay? It says now calculate the correlation between the weight of trash and the number of people, and it gives you a nice hint right here. Use R squared from the figure and take the square root of it. Round to 2 decimal places. So we circled that number up here. We need to take the square root of it, but before you do that, what should you do to that value? Divide it by 100, because we got to turn it back into a decimal. So what we need to take the square root of is this value of 0.605. That's what you need to take the square root of. So what is the square root of 0.065 rounded to 2 decimal places? 0.78. Perfect. Wrong blank. 0.78. Okay. All right, so now we're going to talk about that slope. It says report the slope. For each additional person in the house, there are on average how many additional pounds of trash? All right, so the slope is blank. Well, what was our slope? 9.28. Perfect. 9, it'd be better if I didn't have the eraser on. 9.28. So for each additional person in the house, there are on average blank additional pounds of trash. What goes on the blank? Yeah, be the same slope. Yeah. For every additional person in the house, we have on average 9.28 additional pounds. All right. Either interpret the intercept or explain why it is not appropriate to interpret it. Okay. So A says, one would expect a household with blank persons or people to generate blank pounds of trash. B, for each additional pound of trash, there are /is on average blank additional persons per household. The predicted weight of trash is blank times the number of living people in the household. Or D, it is inappropriate to interpret the intercept because it does not make sense to think of a household with blank people in it generating trash. So let's talk about this intercept. Who's the intercept up here? And the intercept happens when what is 0? Not, well, yeah, the 9.28, or in other words, when people are 0. Okay? So your intercept is whenever x is 0. So when x is 0, how many people does that mean we have? No. 0 people. Because x is about people, right? So when you have 0 people, what's that intercept telling us? Yeah, there's 8.20 pounds of trash. Does that make any sense? No, right? So who should we pick then up here? Does it? Definitely D, because it's inappropriate to think about this, right? That doesn't make any sense. How could I have 8.207 pounds of trash with how many people? 0. That doesn't make any sense. Okay? All right. And number 10. This should end all of the chapter 4 questions. So questions 1 through 10 are all about chapter 4. Actually, no. this starts chapter 6. Just kidding. So questions 1 through 9 are all chapter 4. Starting on question 10 through 20, these are all chapter 6. All right, so it says determine whether the following would be best modeled by continuous or discrete. All right, so is blood sugar level continuous or discrete? Definitely continuous. Definitely continuous, because it's not a hard, fast number. It can be a range of numbers. Is the number of people at a concert continuous or discrete? Definitely discrete. It's like, hey, I've got 10 people at this concert. Or, hey, I've got 11 people at this concert. I can't have anywhere between 10 and 11. I don't have 10.5 people at a concert. That's just weird. What does 0.5 of a person at a concert look like? Just legs walking around? Pretty much. So definitely discrete. The length of a person's hair. Definitely continuous, right? Because, and think about it as I talked to you guys in class. If someone has hair that is 10 inches long and someone that has 11 inches long, is it possible to be between 10 and 11 inches? Absolutely, right? So definitely continuous. I can have lots of different lengths. The number of socks in a drawer. Definitely discrete. I mean, either I have socks in there. Oh, sorry. I marked continuous. Go away, little dot. Definitely discrete. Either I have a certain amount of socks in there or I don't. Okay? Perfect. All right. So right here wants us to find our probabilities. So let's take a look at some things. What do you think the probability of 1 is going to be? Yeah, 0.12. Perfect. What do you think the probability of 6 will be? Yeah, it's going to be the same, right? Okay. Now the question is, what do you think 2, 3, 4, and 5 will be? 0.19. Because if you look at how it's counting, it's right in the middle there, right? And we're counting by 2s. So this would be 0.16. This guy right here would be 0.18. And then you got 0.20. So since we're right between there, this is definitely 0.19, 0.19, 0.19. Whoops, weird looking 9. Change that guy up. And 0.19. Yes?
For the test, will there be like drop-down options?
There are not drop-down options on this one. So it's actually fill in your numbers. Also remember that you can always double check yourself, because if you add all these up, they should add up to the number 1. Okay? Or if you think about these as percents, this is 12%, 19%, 19%, 19, 19, 12. Add all those up, they should add up to 100%. Okay? Yeah, no drop downs on this one, just filling in. Yeah. So, so here, they talk about Eric that wants to go skiing, and he's only going to go if there are inches or more of new snow. And according to the weather report, any amount of new snow between inch and inches, looks like all my numbers are missing. So let's fill in some numbers here. So Eric is only going to go if there are 3 inches or more of new snow. According to the weather report, the amount of new snow will vary between 2 inches and 6 inches. is equally likely. So the probability density curve for tomorrow's new snow is shown. So here's our PDF. And they want us to find the probability that the new snow depth will be 3 inches or more tomorrow. So the first things first, which of these graphs represents the shaded area of 3 inches or more? Definitely A, because A is the one that starts at 3 and goes up. So we're looking at A as our PDF curve. Okay, and then all we're going to do is find the probability for this. And our probability will stay as a decimal, just so you know. All right. Yeah. So how did I tell you, scrolling too much, how did I tell you that we're going to find the area of this curve? Length times width, because really all we're looking at is the area of a rectangle, right? So what is this length that is right there? 3, because you can count it up. From 3 to 4 is 1, 4 to 5 is 2, 5 to 6 is 3. And then what is this length? 0.25. So all we have to do is take these two pieces and multiply them together, because it's the area of a rectangle, and the area of a rectangle is just length times width. And what do we get when we take 3 times 0.25? 0.75 is our probability. Yes. They do not want this as the percent. You'll know if they want the percent, because what they'll do here at the end is they'll put the percent sign if they want the percent. So if you don't see that percent sign there, give it to us as the decimal. Give it to us as the decimal. Okay? Good question. All right, question number 13. So, again, we're talking about that empirical rule that's really kind of going on here. Remember, we discussed the empirical rule quite a bit when we were in that first module of Chapter 1, Chapter 2, and Chapter 3. So the empirical rule roughly applies rough approximations to probabilities of a normal distribution. That's what we're looking at. And so we want to answer questions based on this information. So it says, what percent of z-scores are between 2 standard deviations, -2 to +2? 95. So this is one of those where it is a drop-down menu, so you'll be selecting from the drop-down menu. So you'll be selecting 95, okay? So now it says, roughly, what percentage of z-scores are between 3 standard deviations? Almost all. And we actually know what that percent is. What is the almost all percent? 99.7%. Perfect. So circle almost all. Okay. Roughly what percent of z-scores are between 1 and -1? Yeah, definitely looking at that picture, you can see 68%. Now, what percentage of z-scores are more than 0? 50. Because when you're looking at this guy, you're taking this part of the graph. You want to be more than 0. So how much of my graph is that? It's exactly half of it. You cut it in half at 0. So definitely 50%. And then last but not least, what percentage of z-scores are between 1 and 2? So we come up here, and this time we care about just in here. And remember, we calculated that in class. Do you remember how much that was? 13.5. And again, they give us that drop down, so it's not like you'll have to calculate it, but definitely 13.5. Perfect. Number 14, we're going to do all that again. Do all that again. So this time, We're talking about quantitative scores on a test that are approximately normally distributed with a mean of 500 and a standard deviation of 100. On the horizontal axis of the graph, indicate the test scores that correspond with the provided z-scores. Okay, so the first thing is we're going to take this normal curve that we have here that's been presented in this format. Okay, remember that this first number 0 represents who? The mean, which you will see sometimes called mu. And then the second guy, the 1, represents who? Standard deviation. So that's the normal curve notation. But now they want us to modify it so that it fits our scores. So there's only 3 graphs. So who do you remember goes in the middle? 500. Because that's our mean. So there's only one graph down here that actually fits that description. Woo. Which one is it? A, B, or C? C. So this is our graph, and you can see that it represents the standard deviation of 100 each direction as you start moving as well. All right, so now, again, we just start answering those same questions that we did before, thinking about that empirical rule. What percentage of the students earn quantitative test scores more than 500? 50. Yeah, absolutely. Because if you come up here and look at this graph, we want to be more than 500. So that's half of our graph. Okay. What percentage of test students earn quantitative test scores between 400 and 600? 68, because you are within one standard deviation. 400 and 600. So definitely 68. Okay, what percentage of students earn quantitative test scores more than 800? Yeah, roughly about 0. It's a very, very small percent. Roughly about 0. Definitely. Oops, that was the wrong one. Roughly about 0. All right, let's answer the next guy. What percentage of students earn quantitative test scores less than 200? 0. So I could have left that up there. Roughly what percentage of students earn quantitative test scores between 300 and 700? Say it again. 95, absolutely, because you're within that 2 standard deviations. And last but not least, roughly what percentage of students earn quantitative test scores between 700 and 800? So we're right up here in this small little area right there. It is the 2.5%. Perfect. And again, all this is just coming from that empirical rule that we've been dealing with. Okay? All right, 15. So now we're starting to see what our StatCrunch would kind of kick out. We have 2 figures here, and we're going to use one of these. So IQ scores have a population mean of 100, a population standard deviation of 15, and are approximately normally distributed. Use one of the StatCrunch outputs below to find the probability that a randomly selected person with an IQ of 70 or above, okay, state which figure it is, and then tell us the percent. So which one of these figures, A or B, shows us 70 or above? Definitely B. Whoops. Let's undo that move real quick. Select this guy. Definitely is B. Shows the 70 and above. So based off of that information, it says, tell us the probability, round to 4 decimal places. So what is the probability then? You got it? 0.9772. Perfect. Well, there you go. So from 16 to the end, I believe, yeah. 16 to the end, you're going to be choosing a picture first of what we're dealing with, and then we're going to be finding that probability. So remember that there are 3 ways you can find the probability, that you can use the chart, you can use your calculator, you can use StatCrunch. Okay? And remember that I told you guys in class that I will be giving you the actual z-score chart. So you don't have to worry about any of that if you like to use the chart. So, says use technology to find the indicated information. So A says find the area in a standard normal curve to the left of 1.55. So which of these graphs shows us to the left of 1.55? A is it. That's our graph up to the left of 1.55. So now we want to find that normal curve. So if we go into StatCrunch, how do we start to find that normal curve? Stat. Calculations. Normal. Okay. So what do I have to start putting in? So the mean is 0 because we are normal, right? What's our standard deviation? 1. Good. Do I have to change this guy? No, keep it as the less than, right? Because we want to be to the left. What do I put in there for 0? Or do I change anything? 1.55, perfect. And then now hit compute. So there's that same picture that we talked about. And then right down here, we can see our probability. So what is our, well, let's see what we have to round to first real quick. 4 decimal places? Yep. So 4 decimal places, what is our probability? There you go, 0.9394. .9394. All right. Find the area in the standard curve to the right of 1.55. Remember, the total area under the curve is 1. So which picture represents to the right of 1.55? D. Perfect. And now we want to find that probability. So we could use StatCrunch again. We could use our calculator. Let's use our calculator real quick so that way we can talk about it. And then from here, we'll just switch back and forth between the two. Where do I go on the calculator to find this guy?
Just did 1 minus the first one.
You could also do that too. So what they said is that we could take 1 minus our last answer and get to the right of it. Absolutely, we can do that. But I want to do the calculator real quick. Do you remember where to go on the calculator? All right. Second vars, second variable, that button that's right there. Oops, second variable, because you want to bring up the distribution. That's what DISTR is, distribution. And we've got normal PDF and normal CDF that we talked about in class. Which one are we going to use? The CDF one, because we want to be continuous. So when you bring that up, it starts to bring in all the information we need. So we want to be to the right of 1.55. So what is our lower bound then? It's the smallest number we want to be. If we want to be to the right. Remember, go back to your picture. We circled D. What's our smallest number? Yeah, you're going to start at 1.55. So our smallest number is 1.55. What's the highest number we want to be? Infinity, right? We want to go off to infinity. So remember when we talked about this in class, you'll push 1. We'll get our scientific letter E in there, which you hit second comma, and then put 99. That's what represents positive infinity. If you needed to do negative infinity, you put a -1, E, 99. Okay? And then our mu, is it still 0? Yeah, because we're on the normal curve. And our standard deviation 1? Absolutely. And then so it says paste, and then you're ready to go. And so it tells us that our probability is what to 4 decimal places? You got it. 0.0606. And if you also did 1 minus our previous, which was 0.9493, right? 9394. I know I had it backwards. 9394. Same answer. You could also do that in StatCrunch if you wanted to as well. So 0.0606. And there we go. All right. 17, 18, 19, all these guys are going to be just like what we saw. So it says assume that adults excuse me, adults have IQ scores that are normally distributed with a mean of 105 and a standard deviation of 15. Find the probability that a randomly selected adult has an IQ of 123. Okay. So if we draw our curve, who's in the middle? 105, right? And we're looking to be less than 123. So that means we need to start going in the right direction. So who is the next spot? 120. Because you got to add 15 on, right? Who is the next spot after that? 35. So we know that roughly we're looking for that kind of graph. Okay? So you can do a couple of things for this. You can go into StatCrunch, you can go into your calculator, you can also use the chart. If you're using the chart, you have to convert the 123 into a z-score, and then look it up on the chart, and that will be the answer for it. If you go into StatCrunch, it'll kick out all the information. So let's do StatCrunch on this guy. So we're going to go in, we're going to change some things up. So we're not on the normal curve anymore. So what is the mean?
105.
105. So that's changed a little bit. Our standard deviation is not 1 because we're not on the normal curve. What's our standard deviation? 15. Perfect. Do we want to be less than or greater than?
Less than.
We want to be less than, so we're going to keep that symbol. What do we want to be less than?
123.
123. And now we're ready. And there's that picture that we came up with. And you can see our excuse me, probability, and it wants us to round to 4 decimal places. So what is our probability? 0.8849, perfect. So grabbing my pen. So 0.8849. Yeah. Nothing crazy there. All right, so again, we're back to our pictures. So according to a recent study, the average length of a newborn baby is 18.4 inches with a standard deviation of 0.8 inch. The distribution of lengths is approximately normal. Complete parts A through C. So part A says the probability that a baby will have a length of 19.2 inches or more. So which picture represents 19.2 inches or more? Well, what should we probably do first real quick? Put your mean in the middle, and we can do that. But what if we just want to work with this as the normal without having to do that? What else could we do? Process of elimination, we could do that. But what could we do to the 19.2? We could turn it into what? Turn it into a z-score. And then that will help us know which picture we should look at. Do you remember the formula for z-score? Z equals, yes, your data minus mu over your standard deviation. So minus your mean divided by the standard deviation. So let's take 19.2 minus, what was our mean? 18.4 divided by, what's our standard deviation? I think it was 0.8, 0.8. And what do we get for that number? 1? Perfect. So which picture shows us 1 and above? A. So there you go. Well, there you go. But you could also, if you wanted to, put the 18.4 and then add your standard deviation, which gives you the 19.2. You could have converted it that way too and found that, oh, it has to be graph A. So now we want to figure out the probability. Okay, let's do the calculator this time. Let's do the calculator in this guy. Oops, wrong one. So again, where we're going to go to do this? Second, vars, and who do we want? Normal what? The continuous, 2. Normal CDF. All right, so what's our lowest value? Not our mean. That's not what goes there. Think about your picture. What was our lowest value? Well, 1, that was our z-score. So we can use 1, but we don't have to. 19.2, right? Yeah, we can actually use the number that they gave us, 19.2. And we want to be to the right of that, so do I keep the 1e99? Absolutely, because we want to go to positive infinity. Do I keep my mean at 0? No. What is our mean? That's your 18.4. Yeah, you got it. And then what's our standard deviation? 0.8. So we just paste this information in, and there you go. So it says round to 3 decimal places. So what do we get? .159 is perfect. Yeah. 0.159. Okay. Now this one says, what's the probability that the baby will have a length of 19.9 inches or more? Okay. Which picture do you think this one is? Kind of think about the last one. 19.2 was 1 standard deviation. We shaded to the right. So it's, yeah, this is going to be D, right? Definitely a little bit higher this time. It's a little bit smaller of an area. So we're definitely looking at D this time. And again, you can convert that 19.9 into a z-score and find that it's going to be just a little bit less than 2. Okay, and again, what's the probability? Let's jump into StatCrunch. So StatCrunch, changing some things up. What would we use for the mean?
That's still 18.4.
18.4, perfect. What would we use for the standard deviation?
0.8.
Okay. Do we want less than or greater than?
Greater than.
We want to be greater than this time. Okay. What is our value?
19.9.
And now we compute. So round to 3 decimal places. 0.03, you got it. 0.030. Okay? So 0.030. One more on this one. What's the probability that the baby length will be between 17.1 and 19.4 inches? So which one of these pictures shows between? D. Yeah, you're stuck between two numbers, so we're shading between those two guys. Okay, definitely is D. That shows us between. So now we got to figure out that probability. Let's jump back into the calculator. We'll just keep going back and forth like what we've been doing. So we'll hit second vars, and again, we want to do the normal CDF. What's our lower bound? 17.4 is the lower guy. What's the upper? 19.4. And then it still has the same mean and standard deviation that we had last time. And hit enter. And again, round to 3 decimal places. You got it, 0.789. 0.789. Oops. Perfect. I do want to do the StatCrunch on this one real quick, since it's just a tiny bit different. So in this one, because we are between, you need to make sure that you come up here and you hit the between button. Okay? And you can see how that changes things down here. So our mean and our standard deviation are still good, but notice that in our parenthesis here, this is where you tell it the lower bound and the upper bound. So what was our lower guy again?
17.4.
17.4, and then you click on the upper bound, 19.4, and there it is. And again, it also shows you the picture, which matches what we chose. Cool. All right, almost done. So what we have here, it says in a certain state, the recent critical reading standardized test score was 519. Assume that the standard deviation is 50 and the standardized test scores are normally distributed. Complete parts A through B. Okay, what percentage of the standardized test scores scored less than 500? So we want to choose the picture. And again, they normalize the curve for us. So what can we do to figure this out? How can I figure out which graph it's going to be? Change it to a z-score. And then we know that we want to be less than that score, right? Or, as you mentioned in the last one, what could we do to all these curves? Process of elimination by putting in our actual mean of 513, I think it was. No, 519. And doing your quick standard deviation, kind of figure where things fall. So let's turn it into a z-score again, just kind of do that. So z-score, again, remember that's your data minus mu divided by the standard deviation. So what is our data point? 500. So we'll take 500 minus what is our mu? 519 divided by what's our standard deviation? 50. So we change that to our z-score. What do we get? Negative 0.38. Okay. So we want to be less than this. So which picture shows us less than negative 0.38? Has to be C, because it's on the negative side of the 0. Okay? So then, as usual, this time it wants us to figure out the percentage. Notice you see that percentage sign right here. So that tells us we're definitely going to be working with converting it to the actual percent. Okay? So we are, let's just do the calculator again since we haven't done one to this direction. So again, second distributive. We want continuous. So what is our lower bound this time? What's our smallest value we want to be? It's not 500.
Oh, negative infinity.
Negative infinity, because we are to the left of everything this time. So remember when we talked about this, negative 1, second comma, 99. So that represents our negative infinity. What's our highest we want to be then? 500. Perfect. What is our mean? 519. And what is our standard?
50.
There you go. You could have also used the z-score that you found in here. Your upper would have been the negative 0.38, and then you would have done the normal information right here. So your mean would have been 0, and your standard deviation would have been 1. And what is our percentage? And I believe it says give us 1 decimal place. 1 decimal place. No. Remember, we want the actual percentage this time. So what do we got to do to this to get the percentage first? Let's do that. Times it by 100, right? Now, round it to 1 decimal place. 35.2%. There you go. There you go. So 35.2%. Okay? Now this one says, what's the percentage of standardized test scores that are 519 and more? So which picture represents the 519 and more? Say it again. It's not C. Remember, what's our mean? It's got to be B, right? So we're right there at the mean. We're right there at 0. So it has to be B. Okay? So what's the percentage of that? 50%. Yeah, we don't have to do too much on that one. 50%. And it does say to 1 decimal, so they 0.0. 50.0. Does that make sense? Yeah, 519 was our mean, so we're right there at 0. And we want to be above it, so that's why it was B, because we're above it. And then last but not least, number 20. So the study of a population shows that the male's body temperature are approximately normally distributed with a mean of 98.2 degrees Fahrenheit and a population standard deviation of 0.70 degrees Fahrenheit as well. What body temperature does a male have if he is at the, and we're missing the percentile, 90th percentile? 98th. 98th percentile. All right. So remember, percentiles, what does that mean? So it's the percent, so we want to be 98%, but are we above it or are we below it? You're below. Percentiles mean these are the percentage of people that scored at that or below. Percentiles are where you scored at that or below. So we need a picture that shows us roughly the 98th percentile and below. Where do you think that's going to be? Say it again. It's not C. It's going to be A. Okay? Because the 98th percentile would be a high standard deviation. A high positive standard deviation. Okay? So it is A. So this question is asking us to work backwards because what it wants to know is it wants to know what is the body temperature for the 98th percentile. So again, you can do this a couple different ways. You can use the chart and look for the 98th percent, okay, the one that is closest to that, and find that z-score and then convert it. Can we do that way? Absolutely. I don't have the chart on me, but we can definitely get that chart and look it up. No, that's all right. So let's do that way, though. So I need to pull up a chart. So we need a probability distribution, and we need to look at the images. I should probably say a chart. Probability distribution table. There we go. That's a little bit better. So let's grab this guy. That looks actually kind of ugly. Let's not use that guy. Get something a little bit better. This one looks like what we've been working with. So we're looking for the 98th percentile. So all these are your percentages. Okay? So if we start looking right around and here. Okay? Maybe it'll let me highlight over here. Well, right around in here. I think my cursor should be highlighted. Somewhere in here is our 98%. We want to be as close to 98% as possible. So right here, these two values are really, really close to 98%. This is 0.9803, and this guy right here is 0.9798. Which one is closer to 98%? The 0.9798 or the 0.9803? The 9798. So when we look at this guy, we come over here from 2.0, and that matches up with the 5. So this is 2.05. So our z-score is 2.05. So 98th percentile, the z-score that we just found, 2.05. So all we do is now convert that back into the data information. So 2.05 equals the data that we're looking for minus what's the mu? What's the mean? The mean? 98.2. Sorry, I thought I heard 8.2. 98.2 divided by what's the standard deviation? 0.7. Okay. All right, so all we do is do some cross multiplying. So we want to take 2.05 and multiply it by 0.70. And then you will add 98.2 to that answer. So what is 2.05 times 0.7? Because we're cross multiplying. Because this number is over 1, we're just solving the proportion. 1.435, right? And that's equal to your data minus 98.2. And so like I said, we just add that 98.2 to the other side. So what does that give us? 99.63. And our directions say round to 1 decimal place. So what would that be? 99.6. Now let's talk about if we did our calculators. Okay? So if we did the calculator, we're going to go into second distribute again. Okay? Or second distributed, not distributed, distribution. And you want to do inverse normal because you are trying to go back to your score. So you're going to do inverse normal. And the first thing it says, what's the area? In other words, what's the percent? So what was our percent? No. That was the answer. What was our percentage? What was our percentile? 98. But remember, that's a percent, so we have to change it into a decimal. So 0.98. What was our mean? Because we're not normal. 98 point what? 2. What was our standard deviation? 0.70. And we're going to keep it on the left. And we paste it all in and we hit enter. And there you can see that same answer we came up with. 99.637, blah, 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 blah. Okay, if you did stat crunch, so do our last guy, we do stat crunch. So we put in our mean, which was what? Okay, and our standard deviation. Now this time, we are in standard. Do we want to be greater than or less than?
Below.
We want to be below. We don't know this guy, so we leave it blank. But we do know the percent. What was it again? 0.98. So that's how you input it in StatCrunch, and you hit compute, and it will kick out your number right there. Which again shows us the 99.6 that we got. And that's your test. That's what it's going to be like. Again, I'm just going to go and change the numbers. Questions?